I've made my decision. All right, so uv cosine theta. So the magnitudes multiplied by the cosine of the angle between them. All right, so somehow that works. We'll get to the y in a little bit. So we have this pair of vectors u and v that we're going to call u and v. The dot product u v is equal to the magnitude of u multiplied by the magnitude of v multiplied by the cosine of the angle that separates them. Right? So here we want to find actually the angle between the pair of vectors based on this definition. Right? Now, that's kind of, well, it's one of those things where I suppose you could try to do it in a geometric fashion, but you're gonna make more work for yourself. What I mean by that is by drawing this and drawing that, and then try to somehow find the angle between the two of them. You'd have to isolate what plane they're both living on in order to figure out the angle that separates them. It's doable, but it's not as fun as you might think. So what we're going to do here is manipulate the formula to give us the cosine of theta, which would be equal to uv, u dot v, over the product of the two. And again, I don't really apologize, but some of you already know this, depending on what courses you came from. If you have any kind of background in physics, if you've taken Calc 3, you've seen all this stuff before. But if you don't have any experience in any of that, this is all brand new to you. And so I'm teaching to those people. If you're getting another look at it and it's like, oh yeah, I once knew this, I don't remember all the ins and outs of it, you might find some benefit to it, or maybe you'll learn something that you didn't quite understand before. Anyway, so I got to find the magnitudes, I got to find the dot product, and then do a little trigonometry. You know how I feel about trig. All right, so let's start off with magnitudes. So we have a root 3. Next one is going to be 2 squared plus negative 1 squared. It's going to be 1 anyway, but I'll write it as negative 1 squared plus negative 3 squared. So 4 plus 1 plus 9, so 14 root 14. We need the dot product of u and v. So 1 times 2 plus 1 times, that's poor quality 1, times negative 1 plus 1 times negative 3. So 2 minus 1 minus 3. So negative 2. 2 minus 1 is 1. Minus 3 is negative 2. So cosine of theta is negative 2 over the product of those two magnitudes, which is root 42. Not one of our unit circle numbers. Look at a degree answer. So often forced to work in radians that, why not kick over a little little degree action here. Let me just write the intermediate step, though. I want to get cosine gone from the left, so that means I'm going to take the inverse cosine of both sides. All right, so theta is going to be equal to the inverse cosine of -2 over root 42. Inverse cosine. Put in the fraction. You don't really need to. It just looks nicer. (107.9), so about 108 degrees. All right, so the inverse cosine domain is between 0 and pi, so 0 and 180 degrees. So we're looking at a negative ratio, so that should put you in the second quadrant. So an angle between 90 and 180 degrees is expected. If you got something other than that, it would be alarming. Also, if you think about a vector, it's going to create some kind of V shape. It's just a question of, if you're in 2 space or 3 space, you have 2 angles. The shorter angle that gets you from one vector to the other, or I think it's called an explementary angle. That's the 2 angles that sum up to 360 degrees. I remember looking it up at one point because it's like so rare. Nobody ever needs to know the word for it. But it was a question of curiosity in one class, and I was like, let's just look it up. I think it's complementary goes to 90, supplementary to 180, and I think it's explementary that goes to 360. But if I'm going to define an angle between 2 vectors, if I don't have any context, I'm going to take the shorter of the 2 vectors. Right? I'm not going to say, what would it be, 252 degrees? What's the difference? It's you get the same job done with 108. Well, actually, it'd be -252. So that's right. But yeah, this gets the job done. Now, if you're talking about a particular form of rotation, you need to go in a particular direction, or circumstances are forcing you to avoid something. I call it the Medusa Concept, which is like, I need to turn around, so I need to do a 180-degree turn. But if I turn that way, I'm going to look at Medusa and turn to stone. So I'll go the other way. So in that case, I'd choose to go negative 180 degrees as opposed to positive 180 degrees. Okay, so all stuff that but the idea is, you should have a reason why you're going in a direction other than the one that's stated by the domain of whatever the function is. Now, if you're doing an inverse sine function, the domain for that is -90 to 90. Right? Now, there are many circumstances in which you wouldn't want to go in a negative angular direction. Right? So in that case, you may want to say you're looking at a domain between 270 and 360 just to make it positive values, but it all depends on the situation. So the next one's along the same lines, so I'll just pop a star on that one. Orthogonal vectors. All right, so orthogonal is kind of another term for perpendicular, or at least conceptually the same idea as perpendicular. But it allows for that relationship to occur for things that aren't just lines. Right? So if you're talking about planes, for example, 2 planes that are orthogonal, they're going to intersect, forming 90-degree angles, but they're not lines, so we wouldn't say perpendicular. Now, that being said, just to make things as confusing as possible, the symbol for orthogonal is still the upside down T. Right? So it makes you think it's exactly the same thing. conceptually, a good working definition is perpendicular, because I don't think anybody's ever limited themselves to lines as being the only application of the term perpendicular. If I were to say that the ceiling, the floor, and the wall are perpendicular to one another, you'd say, of course. Technically, they're not, because they're not lines, right? But if I were to say one path along the floor and the wall is they're perpendicular, that would be a true statement. Now, if I were to say that they're orthogonal, floor and wall, that would be a true statement, right? But nobody's losing any sleep over whether somebody says perpendicular or orthogonal. Now, the vectors themselves, we can use the term perpendicular to make that determination, but orthogonal is a catch-all that allows you to compare a line and a plane, two planes to one another, right? Two surfaces to one another. So if you have something that's, some sort of three-dimensional surface, like the sphere, there could be a plane that intersects the sphere in such a way that it forms an orthogonal relationship. But you're not talking about something that's linear. It's just at that particular point, the tangent plane to the sphere would be orthogonal to the tangent that's intersecting the sphere. All right. So there's a lot of different applications to the word orthogonal. You're sort of limited if you say the word perpendicular. But like I said, nobody's crying one way or the other. So determine whether A and B are orthogonal vectors. Now, I gave the relationship there, but let's kind of step away from that for a second. Let's actually go back to the whole magnitude idea. So I'll find the magnitude of A, the magnitude of B, and the dot product of A and B. We're just going to find the angle separating these two vectors. All right. So magnitude of A, 1 squared plus 0 squared plus 5 squared. Root 26. 10 squared plus 3 squared plus negative 2 squared. 113. $100 plus 9 plus 4. I hope it's right. Oh, I don't want to be wrong again. So we have 10 plus 0 minus 10, result 0. So that's our dot product component, right? Now the cosine of theta is equal to A dot B over the two magnitudes multiplied. So 0 over root 26 root 113. So that tells me that the cosine of theta is equal to 0. Showing all the gory details here. And take the inverse cosine on both sides. Take the inverse cosine, and I get theta equals the inverse cosine of 0. What is the inverse cosine of 0? 90 degrees. So therefore we have a right angle between vectors A and B, which means A is orthogonal to B. All right. Now you say, well, why'd you do all that if you could have just followed this rule? Well, all of this justifies why that rule exists, right? Because if you just kind of take it just going right back to the rule itself. UV, U dot V is equal to the magnitudes multiplied by the cosine of theta. So the angle separating them. So if we let the angle separating the two vectors be equal to 90 degrees, then we're looking at UV, U dot V, multiplied by V, and the cosine of 90. And 0, and the cosine of 90 is equal to 0, so the result is equal to 0. All right. So how does that relate to this? Well, here's the dot product between the two vectors. It gives us a numerator equal to 0. It tells us that no matter what those magnitudes were, as ugly as they were, the whole thing's going to zero out if the dot product is equal to 0, which makes the cosine equal to 0, which makes the angle equal to 90 in all cases. All right, so say that again. Orthogonal. Yep. Well, this is the rule that justifies the dot product of U and V. That shows why the dot product of U and V would be equal to 0, giving us something as orthogonal. Right? We're establishing that it's a 90-degree vector relationship. All right. So